All right. Class. Joseph. Yeah. Okay. Okay. All right. So, uh, like I was saying, optimization. This one right here. We're gonna have one example for the notes, and then you guys are gonna do the notes, the homework that goes exactly with those notes. So, I'm gonna try and finish off as the notes quickly as I can. Go through it so you will have time to actually work on this. So hopefully everyone will be able to get through this. So let's see right here. So optimization. Now, what do you think optimization means? Anyone? Optimize. Okay. When we're talking about derivatives recently, what were we trying to actually figure out every single time? Min and the min and max, right? So let's say, whoa, dude, min and max. So min and max. So if I have a business, let's say for instance I am running some type of business. Okay, I am not cooking meth. Has nothing to do with meth. I don't know why you guys mentioned about cooking meth, but yeah. So if I in that business, I am going to maximize profits, right? I'm going to minimize. What would I minimize? Cost. Cost to actually make it. So I want to minimize cost to make whatever it is because that's going to make me more money. I'm going to maximize my profits by selling it at the optimal amount, not below, but at the optimal amount. So that's where our derivatives come into play for these. So every single one of these, this is a step-by-step how to do everything here. So as you read one of these problems, you say, read the problem until you understand and can identify the quantity for which the maximum or minimum value is being found. Assign a symbol to represent that. Assign symbols to represent the other variables in the problem if possible. Draw a picture and label it. Determine relationships. Okay, this draw a picture I think is probably one of the better things you will do. I am a visual person. I have to see something. Determine relationships among the variables. Express the quantity to be maximized or minimized as a function of one of the variables. And determine a meaningful domain for the function. Now, that's important. So, meaningful domain. I'm going to talk about number of people on an airplane. My domain. What number set would I be dealing with number of people on a plane? 0 to infinity, right? Am I dealing with negative numbers? No. I don't have negative number of people. I can have a negative person. Okay? Those people are just, you can never make them happy, right, Anthony? Yeah, they're just always negative. Okay? But there is not a negative number. So I go 0 to positive numbers. Now, I have a really, really, really short person. Am I going to consider that person half a person? No. A person is a person no matter how small. So, that's one of the things you actually have to take into account when you're dealing with these things right here. And I'm talking about my domain. It's going to be whole numbers. That's my number set. It's the whole numbers. Okay, and then 5 absolute maximum or absolute minimum for the value of the function. A farmer. So we're maximizing the area, right? So that means what type of formula or equation should I have to do? A what? Very good. I'm going to have an area problem. So I have a diagram right here. A farmer with 400 meters of fencing wants to enclose a rectangular plot that borders a straight river. The farmer does not fence the side along the river. What is the largest rectangular area that can be enclosed? Okay, so now thinking about that. I'm going to have an area, right? I'm trying to maximize the area, which is here. So to get the area, what would my formula to be the area be? In this sense right here. X times y, right? So my area so I'm going to maximize that area. And the restrictions I have. Let's talk about what it is that I can maximize this however I want. But now I have to have some type of limitations to go along with this. What is my limitation to go along with this? 4,000 meters of fencing. Now, what type of unit is fencing going to be? All right, think about a fence. Does it take up area? No. What does it do? What does a fence do? It's the perimeter. Very good. It goes around the outside, right? It doesn't go through the middle. It doesn't fill up the space. It is my perimeter. So my perimeter. So I'm going to have another function to go along with this to help maximize. So whenever I do this, I should have two or more type of equations that are going to go together to maximize this. Are you okay, Blake? What happened to you with what? Linear, which has to do with my perimeter. My perimeter would be like the circumference around the outside, right? The fence around the outside. So what's the formula for the perimeter? My perimeter 2x plus y. Why is it not 2y? Why is it not 2y? Very good. I'm not fencing along the river. Okay, so now I have it set up and both these together. So basically, I have to use the perimeter formula to plug in the area to give me my maximum. So let's see. So my perimeter, which is 4,000, Karen, did you grab notes? They're up there. Now, let's look at my area formula now. I have all this over here set up. This is going to help me solve for this. Now, in that area formula, I have three variables. I know I need to maximize this. I need to maximize this, right? So I know that when I take the derivative, it must be equal to 0 at some point, right? Yes. That's what I'm looking for. I'm looking for the derivative to be equal to 0 at some point. But I also have an x and a y. I'm going to use substitution and my perimeter formula to get rid of one of those variables. I'm going to isolate to get one of the variables gone. I'm going to replace the y. What can I replace the y with if I am using this as a substitution? I can say y is equal to yes, 4,000 minus 2x. Just by subtracting my 2x from both sides, right? Now, that's going to go into this side over here. A is equal to x times 4,000 minus 2x. So that's going to help me out. So now let's say I'm going to distribute that. So A is equal to 4,000 x minus 2x squared. And this is the formula for my area. So what type of shape is this going to give me? It's a parabola, isn't it? Very good. It's a negative. My parabola is negative. So that means it's going to be opening up down, right? Okay, so it's going to be concave down, but if it's concave down, what does that give me? Maximum. Very good. That's what I'm looking for. So as I'm doing my math, I'm looking at this and seeing what I'm getting. I'm maximizing the area in this one, right? Because there's going to be problems that you're going to have multiple zeros. One might be a minimum, one might be a maximum. Okay, but in this problem right here, we only have a maximum because it comes out to be a parabola that's upside down. All right, let's go ahead. So it would be a prime of x is equal to 4,000 minus 4x. Now, the whole point of trying to do this is we know that our derivative has to be equal to 0. So I'm going to set this equals 0. So I'm going to say 0 equals 4,000 minus 4x. Do a little bit of algebra back and forth, and so you could say x equals positive. Because you're going to subtract 4,000 from both sides, right? You're subtracting and then dividing by 4, so you're going to get x equals 1,000. All right, so let's take a look. So if x equals 1,000, so that means that there's 1,000 right here. There's 1,000 right here. So what's in that middle? 2,000, right? Because all together has to add up to 4,000. So that means that my y value and let's go back to the question. Now that I solved for everything, what is the largest rectangular area that can be enclosed? So, yeah. So it would be my area is equal to my x value, which was 1,000, times my y value, which is 2,000, yes, that's using all of it. So there is, you could use less than it, but that wouldn't maximize it. to show you. I'm going to pull up the graph. Dude, it's not. All right, so you ready? So I'm gonna show you something. So, but I'm gonna reduce it by 100 each way. So instead of saying my 1,000, which I know is gonna maximize because I did the math, right? So let's say it's 900. But since it's instead of 1,000 here, right? It's 900. So I'm actually that extra 100. I'm adding it to the other side. So instead of being 2,000, it's 2,100 now, right? Okay, so 2,100. Okay, e to the 6 means million. Okay, so wait, e to the 6 million. Is that less than what I had with what I had before? This is 1.89 million. It's less because I had 2 million, right? What's the other way? Okay, let's switch it up. Instead of going with 900, I'm now going to go 1,100. Okay, so I'm going 1,100, and so it'd be right here. And so if it's 1,100, 1,100, I'm going to subtract, was it 200 from that one? So it's instead of 2,000, it should be 18. 18, right? All right. Was that one less than my 2 million? It's less than 2 million. So by going either side of this, the most I could get in general is actually my 2 million. Because that's what we plugged in. Yeah. Okay. So are you saying try to make it others? Okay, let's try it out. If I were to use all 4,000 meters, and instead of actually making it a big area, I just make it a long rectangle. Okay, let's say it's just 1 meter here, 1 meter here. So that means it's going to be 39,399 feet. What would be the maximum area if I use more of the river? because it's just this times this, right? Okay, so this is the river right here. And so change my x to 1, right? And just make it a really, really long rectangle. And then by whatever fencing is left, I'm left with my max area is 3998. Is that a lot less than my 2 million meters squared? No, it is. And so you can keep playing with this, with the numbers over and over again to get to see what you're going to have. Perfect. That's it right there. That's it. Yes. All right. So that being said, we're going to use the rest of this time here, and you guys are going to work on number 1, 3, and 5. Those are all using the same steps.